Today we're going to look at chemistry. And chemistry can actually be broken down into basic chemistry and biochemistry. Let's look first at basic chemistry. And for basic chemistry, the building blocks of matter are atoms. What is matter? Well, that's anything that has mass and occupies space or has volume. And weight and volume are different. Weight is the mass plus the effects of gravity. So a person's weight on Earth is different than it would be on another planet because the amount of gravity on those planets are different. Volume is the amount of space that a substance or object occupies, or that is enclosed within a container. Let's look at some examples of matter. The three states are solid, liquid, and gas. Solids have a definite shape and volume. Liquids have a definite volume but changeable shape, and gases have changeable shape and volume. The reason a solid has a definite shape and volume is because it's rigid. No matter what container you put it in, it keeps that rigid shape and the amount doesn't change. A liquid has a definite volume but changeable shape. The amount doesn't change regardless of the container you put it in, but the shape does. And a gas has a changeable shape and volume because gas can be compressed or pressurized. The air we breathe is a great example. But what about the composition of matter? Well, all matter is composed of elements, which are made up completely of one type of atom, all with the same number of protons. The periodic table at present recognizes 118 elements. That's the complete list of elements as it currently stands. There are 6 elements that make up 96% of the human body. They are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And you can see next to each one of those words is its chemical symbol that you would see on the periodic table. Carbon, hydrogen, oxygen, and nitrogen, they make up most of the human body, whereas phosphorus and sulfur are found in trace or smaller amounts. But regardless, every element is composed of atoms. All those atoms have the same number of protons, and those elements' atoms differ from those of other elements. And the atoms of certain elements share physical and chemical properties like texture, color, how reactive they are, what other types of atoms or how many bonds they like to form. So let's look at the atom a little bit closer. What is an atom? Well, it's the smallest unit of an element. That makes sense. We've talked about that. Elements are composed of atoms of one type. But we need to look closer at what is an individual atom made up of. It's made up of a group of things called subatomic particles. The subatomic particles are neutrons, protons, and electrons. Neutrons are uncharged or neutral. Protons are positively charged, and electrons are negatively charged. So on the periodic table, since it's representing neutral atoms, those atoms that are making up elements have the same number of positive and negative charges or the same number of protons and electrons. So as a whole, atoms are neutral because the charges balance each other. An atom is also composed of 2 regions. These are the areas where you find the subatomic particles. You find protons and neutrons in the nucleus, in the center. You find electrons in the electron shells or orbitals, which circle or go around the nucleus. So atoms are made up of protons and neutrons and electrons. They exist in different locations. And if we were to add the mass of each atom together, we would actually be looking at just the protons and neutrons. Even though they're small, they're bigger than electrons, and they're all that is added together to get the mass of an atom. So that's why the mass of an atom, again, is equal to the number of protons and neutrons in that atom. So let's look at atomic structure in a little bit more detail. The mass of an atom is given an arbitrary measurement known as atomic mass unit. Because only protons and neutrons weigh something, atomically, we give them a 1 AMU, or 1 atomic mass unit. Notice they're also both found in the nucleus, but their charge differs. Protons are positive, and neutrons are neutral, or carry a non-charge. Electrons, however, are negative, and we know they hang out in the orbitals, and they're so small, we don't say they weigh anything. We give them a 0 AMU. or atomic mass unit. So let's look at where the subatomic particles are located again. Here we're looking at A hydrogen atom, and B, a helium atom. The hydrogen atom is simpler than the helium atom. Hydrogen is so simple that it's only made up of one proton sitting in the atomic nucleus and one electron sitting in the first orbital, or electron shell. Over on the right, B, we're looking at helium. Helium has two protons, two neutrons, and two electrons. So that means that not only is it atomically neutral, just like hydrogen, it also contains all three of the subatomic particles. So this is the general layout for an atom. Protons and neutrons in the nucleus, electrons in orbitals surrounding the nucleus. Here are three more examples. Again, these are the smallest atoms. You have hydrogen, helium, and lithium. We've already looked at hydrogen and helium, so let's focus on lithium. Lithium has 3 protons, 4 neutrons, and 3 electrons. Notice that the red protons and yellow neutrons are in the nucleus, whereas the electrons are in orbitals. The first orbital for all atoms likes to hold 2 electrons, and the other electrons tend to distribute themselves in further orbitals. So again, let's define an atom. It is the smallest unit that can exist as an element, and it still has the properties of that element. But elements themselves are made up of many atoms of the same type. On the periodic table, we would use chemical symbols like C for carbon or K for potassium, and information that you would find on the periodic table with the atomic symbol or chemical symbol is the atomic number. The atomic number is letting you know how many protons are in a neutral atom. And the atomic mass is an average of all isotopes of that particular chemical, and that average is generally closest to the most common isotope. And it's an average of how many protons and neutrons are in an atom. So here's our quick guide. We're assuming, unless told otherwise, that all atoms are neutral or uncharged, meaning they have the same number of protons and electrons. We're going to talk more about chemical bonding, and electrons determine the vast majority of physical properties and how exactly electrons are going to interact with other atoms. The atomic number is unique to each type of atom, and that's because the atomic number is the number of protons in the nucleus, and how many protons an atom has determines what type of chemical element it is. If you wanted to write the chemical symbol and include the atomic symbol, you would write the letter of the chemical symbol first, or letters, and then you would put the atomic number before it as a subscript, as a small number below it. And on the periodic table, this information is arranged differently, but if you were writing a paper or an article, this is the easiest way to write the atomic number included with a chemical symbol. Remember, mass number is the total number of protons and neutrons in the nucleus. So if you wanted to get the mass of an atom, you just add how many protons and how many neutrons together. But if you wanted to write mass number, say writing a paper or a column, you'd write it before the chemical symbol as a superscript, or as a small number a little bit above but before the chemical or atomic symbol. An atomic weight is an average of the mass numbers of all isotopes. It ends up looking pretty close to the mass number, but is slightly different because we have to count for all different types of that variation of atom. So we can see here on the periodic table of elements that we have numbered elements, and the numbers increase as we go down. So the smaller atoms are up top, bigger ones are below. There's some differences here where you would take and go down to this grouping when you get to particular parts. And we'll examine the periodic table in a little bit more detail later on. So more on the subatomic particles. Let's just make sure everything's very clear. So protons determine what element you're looking at. An element is made up of the same type of atoms, all with the same number of proton. And generally, protons are balanced with the number of electrons. That's what makes atoms electrically neutral. This can change Electrons can be gained or lost, changing the charge of an atom, but that's only under certain circumstances and usually when forming a chemical bond. So, unless told otherwise, unless we're told about reactivity or the forming of an ionic or covalent bond, we're going to assume that the number of electrons and the number of protons are equal, and that the protons and neutrons are hanging out in the nucleus, and the electrons in the orbitals are playing their role in atoms. The nucleus provides stability, whereas the electrons are more dynamic. They can move around, they're very quickly moving around the nucleus in orbitals, and that allows them to capture and release energy, and that means they're the main components of forming bonds or linking atoms. So electrons can occupy many electron shells, or orbitals. They give atoms a three-dimensional shape, they're in three-dimensional regions around the nucleus, and each level or orbital has a specific energy. And as you move farther away from the nucleus, the electrons gain or have a higher amount of energy that is stored. So for example, here, carbon, we can count them, has 1, 2, 3, 4 electrons in its outermost energy shell or orbital, and only 2 in the first one. And notice that that 2 rule in the first orbital carries over into all of the other atoms: oxygen, phosphorus, and calcium. And we'll see that's the case for all atoms, that 2 electrons tend to occupy the first orbital, and then we tend to see 8 or more in the following orbitals. So here we have 4 for carbon. More could fit. 1, 2, 3, 4, 5. We get 6 for oxygen. For phosphorus, we get 1, 2, 3, 4, 5, 6, 7, 8. And notice there's still more electrons, but after 8, we move into the next orbital. So for the most part, we're going to use a general octet rule, which applies to the second orbital and out, where we tend to see 8 electrons fill up the orbitals other than the first, which holds 2. And that's because each electron shell holds a specific number of electrons. The shell nearest the nucleus can only hold up to 2, whereas more distant shells can hold up to 8. Some hold up to more than just 8, and electrons will fill lowest energy level shells or nearest the nucleus first before moving outward. So there is some organization here to the subatomic particles, specifically the electrons, and how they function. And as atomic number increases, meaning as the number of protons in an atom increases, we're actually looking at different elements, and the electron shells fill increasingly, and we get more and more orbitals for bigger atoms. But regardless of the number of electrons in a chemically neutral atom, protons and electrons are balanced. Earlier I mentioned isotopes, especially when we were looking at atomic weight. There are actually different types of atoms or isotopes of the same element. And these are atoms of the same elements. They have the same number of protons, but they're differing in number of neutrons. And certain isotopes are more common than others, but you still have to average their mass together to get the average weight for how many of a certain atom exist in nature. So atoms of the same element with different number of neutrons are isotopes. Notice that's red, it's an important definition to know. And this is distinguished by different mass numbers because protons plus neutrons will give you the mass number for an atom. And if you're changing the number of neutrons, that's changing the mass number. For example, let's look at isotopes of hydrogen. So the atomic weight of hydrogen is 1.008 on average, and that reveals that its lightest isotope, which is right here, the one we're used to calling hydrogen, but it's hydrogen 1 with 1 proton, no neutrons, and 1 electron, that it's present in much greater amounts in our world than the other 2 forms. Deuterium and tritium do exist, but they're really rare. You're more likely to come into contact with hydrogen 1 than hydrogen 2 or 3. And that's why when you take the average of their mass, the average looks closer to hydrogen 1. Think of it this way. You have a classroom of 100 people, and everyone makes A's except for 2 people. One person makes a D, the other one makes an F. But when you take the average of the grades for that class to produce a class average, the average is going to look more like an A than the D or the F. because they're going to play a smaller role when being incorporated in that average. The same thing is happening with isotopes. Very few deuterium or tritium naturally in the environment. So when you take the average and you're adding all the possible hydrogens that exist environmentally, and they mostly exist like hydrogen 1, the atomic weight is going to look like that atomic mass. So let's test yourself. First, let's see question 1. All atoms of the same element have the same number of protons. The smallest unit of an element is a atom. And atoms are composed of which 3 subatomic particles? The subatomic particles are protons, neutrons, and electrons. How about this last question? Each of 2 or more forms of the same element that contain equal numbers of protons but different number of neutrons is called a or an isotope. So this is a great study slide. Make sure you know that all atoms of the same element are protons. Atoms are the smallest structural and functional unit of matter. Protons, neutrons, and electrons collectively can be called subatomic particles. And if you have the same number of protons, but the atoms have different number of neutrons, not only does that change their atomic mass, it means they're isotopes. So here's a good summary slide in case you need to do any calculations for figuring out not only atomic mass, but number of protons, neutrons, or electrons. If you need to figure out the atomic number, easy, just look for the number of protons. Or maybe you know the number of protons and you're asked for atomic number. It's the same thing. What about if you're looking for the number of electrons? Well, the number of electrons should equal the number of protons in a neutral atom. So if you know atomic number or number of protons, you know the number of electrons, and vice versa. What if you're looking for the number of neutrons? Well, just take mass number minus atomic number, because number of neutrons plus number of protons is mass number, and atomic number is number of protons. So you could rewrite that equation, and to look for the number of neutrons, it'd be mass number minus the number of protons. So let's look at an example. For oxygen, the number of protons is the same thing as atomic number, and you'd be given 8 as the number of protons, so you automatically know the atomic number as well. Well, what if you're looking for the number of electrons? Well, oxygen here is neutral, so the number of protons and electrons are the same, and proton is the same as atomic number, so also 8. And if you're looking for the number of neutrons, you have to take mass number, which is usually given to you in an equation, or you can look to the periodic table. The mass number for oxygen is 16. You just do 16 minus 8, because that's the atomic number or number of protons, and the answer there is also 8. Well, what happens when we put atoms together, or elements together? We form molecules and compounds, because most atoms do not exist in the free state. They're actually chemically combined with other atoms. And a compound is actually a type of molecule. A molecule is just a general term for 2 or more atoms bonded together. You can have something like oxygen gas, which is 2 oxygen atoms bonded together. Or water, which is 2 hydrogen to 1 oxygen bonded together. If you use the term compound, you're being a little bit more specific. It's a type of molecule that has 2 or more different kinds of atoms bonded together. They're chemically pure. All molecules are identical. For example, water is an example of a compound. It's made up of not just oxygen or not just hydrogen, but actually oxygen and hydrogen. So 2 different types of atoms. And the 2 hydrogen are bonded to the 1 oxygen. Carbon monoxide and sodium chloride are other examples. Sodium chloride is just table salt. So molecules with only one type of atom are just called molecules, whereas if you have 2 or more different kinds of atoms bonded together, that would be a compound. So a compound's really just a type of molecule. Molecules and compounds do have abbreviations just like elements, and these are called chemical formulas. They include letters and numbers. The letters stand for different atoms. The numbers that appear as subscripts indicate how many of these atoms are in the molecule or compound. And if there's no subscript that appears after the atom, we know there's just only one of that type in the molecule or molecular compound. So here are some examples. CO2 is carbon dioxide. CH4 is methane. N2 is nitrogen gas. H2 is hydrogen gas. And C6H12O6 is glucose. For a minute, let's take a closer look at glucose. C6 with a subscript of 6 after the letter means there are 6 carbon. H12, another subscript after the letter, means that there are 12 hydrogen. And again, O6 with a 6 subscript means there is 6 oxygen. What if we put a 2 right in front of the C? Well, generally that would mean there are 2 glucose molecules, both with 6 carbon, 12 hydrogen, and 6 oxygen. Let's talk about making chemical bonds or putting atoms together. Most atoms are unstable in their natural state or free, so they don't like being all alone. They want to react with each other or link together, become more stable. And these chemical bonds share an energy relationship. And it's electrons that are going to be involved in chemical reactions. So they're the ones, the electrons, that determine whether or not a chemical reaction will take place, and if so, what type of chemical bond is formed. For that reason, we're interested in how electrons occupy energy shells, or orbitals. These orbitals can also be taught or thought of as energy levels. And in order to look at them, we have to establish a rule, and that rule is the octet rule. And this octet rule is except for the first shell, which is full with 2 electrons, atoms tend to interact using their electrons in a way that 8 or more electrons fill up outermost energy shells. The octet rule is also known as the rule of 8s. And more simplified, it says that atoms desire 8 electrons in their valence shell. What's a valence shell? Well, it's the outermost orbital or electron shell. There's exceptions to the atoms desire 8 rule, and that is only with the first orbital closest to the nucleus, and that orbital only wants 2 electrons. But otherwise, we see that atoms desire to have 8 electrons, and that's the driving force behind chemical reactions. For example, noble gases, which you can find on the periodic table, they already have a full 8 electrons in their valence shell, or their outermost energy level already has 8 electrons, so they're stable and happy, therefore not chemically reactive. But most atoms don't have that full 8 electrons in their valence shell, meaning they would like to gain, lose, or share electrons or form a bond with other atoms in order to achieve this chemical stability and become chemically non-reactive. So most atoms are looking for that 8 electrons in the valence shell, however they can get it. Here are the noble gases on the periodic table. So helium, neon, argon, krypton, xenon, and radon all have 8 electrons in their valence shell. Here's another example of chemically inert elements. So helium and neon, we have their orbital models drawn out. Helium has 1 orbital, and that first orbital closest to the nucleus is satisfied with 2 electrons. So helium is inert or not chemically reactive. Neon is also inert or not chemically reactive. Notice that it has more than 1 orbital, but the first one's satisfied, and the second one has 1, 2, 3, 4, 5, 6, 7, 8 electrons, meaning that the outermost energy level or valence shell for both of these atoms is complete, making them non-reactive. Here are some chemically reactive elements. And notice that their outermost energy level is not complete, it's incomplete. Their valence shell are missing electrons, or at least as far as they're concerned for stability. Here's hydrogen with its 1 electron. It has 1 orbital close to the nucleus, so it would like 2. Carbon here has 4 electrons in its valence shell. It would like 4 more. And as a result, carbon likes to form 4 bonds in order to share or get more electrons. Oxygen has 6 in its valence shell, and sodium has 1. They would all like more or to give away electrons in order to stabilize themselves, So they're reactive. They can form or tend to form bonds. Well, what types of chemical bonds? Well, electrons interact with other atoms and are therefore the subatomic particle most involved in chemical bonding. And the types of bonds they tend to form are ionic, covalent, or there's a smaller interaction we call a hydrogen bond that we'll look at. But ionic and covalent will be our main focus. And when we consider bonding behavior, remember to focus on the electrons, focus on the outermost energy level or valence shell, and remember the rule of 8, or the fact that the outermost energy level, except for that first one, would like 8 electrons in order to stabilize the atom and make it unreactive. The noble gases are the only ones that tend to be inert themselves, naturally having a valence shell with 8 electrons. But those with fewer than 8 electrons in their valence shell want to gain, lose, or even share electrons to become stable, and those are the atoms that are reactive and going to be performing or participating in chemical bonding. Let's look at ionic bonds first. So most ionic bonds do fall into the category of salts because you'll have something that's an electron acceptor, something that's an electron donor. Sodium chloride or table salt's a great example of forming ionic bonds. Ions, when separated or when you take a salt and dissolve it in water, tend to be charged. Ions are charged atoms that are results of the gain or loss of an electron. And that means that there has to be a transfer. If one atom's gaining and one atom is losing an electron, there's a transfer of one or more electrons, and that results in the charge. One becomes an anion, and the other becomes a cation. Anions have a negative charge because they're the atom that gained one or more electrons, whereas the one that becomes a cation has a positive charge because they were the atom that lost one or more electrons. And neutral atoms that lose electrons have their protons still, making them more positive. Neutral atoms that gain electrons only have their protons and electrons but gained more, making them negative. A way to remember that anions get the negative charge is if you get bit by an ant, it's a negative experience. Whereas cations, think of kittens or cats, someone hands you a cat, it's a more positive experience. So keep in mind that with ionic bonds, there is a electron transfer. One atom becomes positive, one becomes negative. The negative is the one that gained electrons, the positive the one that lost. And while one atom gains electrons and the other atom loses electrons, once we create the ions, they have an attraction to each other, and in a dry environment, tend to form salts or crystals. So here's just another way to look at that. So if the number of electrons is less than the number of protons, you think it's the cation or the anion? It's the cation, and so that would be a positive atom in that situation. We can even count over here. We have 1, 2, 3, 4, 5 protons, 1, 2, 3 electrons. So if we were trying to figure out the charge, we have 3 protons and 3 electrons that would cancel each other out, but 2 extra protons. So this atom would have a positive 2 charge. When we have number of electrons is more than the number of protons, then we're looking at the anion. So we have here 3 protons and 3 electrons that would cancel each other out. We have 2 extra electrons that don't cancel, meaning that this anion would have a negative 2 charge because protons have positive charges and electrons have negative charges. Let's look at the formation of ionic bond using sodium and chloride, or what generates table salt. Notice that before the ionic bond forms, sodium has 1 electron in its outermost shell, and it would like 8. Chlorine has 7 electrons in its outermost shell, and it would like 8. It's a lot easier for sodium to give up its 1 electron and donate it to chlorine, making both of these atoms happy, than it would be for sodium to gain 7 electrons. So that's exactly what sodium does. It gives up its 1 valence electron to chlorine, meaning chlorine now has 8 valence shell electrons, but it gained an electron, making it negative. Sodium lost an electron, So now it has more protons, making it positive, but now its outermost shell is the second, and that has 8 electrons already, so it's also happy and stable. When dissolved in water, sodium chloride actually carry charge. Sodium and chloride would carry opposite charges, but when desiccated or in a dry environment, they would form crystals. And most ionic compounds are salt because of that characteristic, where when dry, the salts form crystals instead of individual molecules. A great example is always going to be sodium chloride or table salt, because when dissolved in water, they dissociate or break apart into ions. And ions are positively or negatively charged atoms that result from the transfer of electrons during the formation of an ionic bond. Here's the formation of an ionic bond in a desiccated environment. Here's the crystal structure for sodium chloride. So you can see we have an organized chloride and sodium back and forth arrangement. And this would break down and the charges would be more present if it was dissolved in water. Next, let's look at covalent bonds. Covalent bonds are formed by sharing 2 or more valence shell electrons. Not transfer, sharing. So you can share a pair, not just one electron. So more than one pair of electrons could be shared. If you share 2, it's a single bond. If you share 4, it's a double bond. If you share 6, it's a triple bond. If you share 6, it's 3 pairs. If you share 4, it's 2 pairs. If you share 2, that's 1 pair. That's how we're getting single, double, and triple from 2, 4, and 6. And this allows each atom to fill its valence shell at least part of the time. And there are 2 types of covalent bonds, polar and nonpolar covalent bonds. So let's look at the formation of a covalent bond. Here you have carbon. It has 4 electrons in its valence shell. It would like 8. And if it forms a bond with 4 hydrogen, which has 1 valence shell electron, and in this first shell it would like 2, both can be happy and stable. Because if you share electrons, you get to count both electrons for both atoms. So for carbon, in the outermost shell, I get to count these 2, these as well, and finally these 2. So there's 1, 2, 3, 4, 5, 6, 7, 8 for carbon. But again, we're sharing, so I get to count the pairs for both atoms. So this hydrogen has 2. It's happy. The same can be said for this hydrogen, this one, and finally this one. And I could denote the pair, or the 2 electrons being shared, with a line to represent a single bond. Here we'll see double bonds. So we have 4 electrons making up 2 pairs being shared between oxygen atoms. Here we have 6 electrons, or 3 pairs, being shared between nitrogen atoms, represented by 3 lines. And in all of these examples of the formation of covalent bonds, they're sharing in order to satisfy the octet rule, or to get 8 electrons in their outermost energy level, or valence shell. If we were to share electrons equally or unequally, it matters in covalent bonds. Equal sharing produces electrically balanced or nonpolar molecules, whereas unequal sharing produces polar molecules. These unequally shared polar molecules do have electron attracting abilities that are different on each side. So here's an example of equal sharing of electrons. This is a nonpolar molecule. Carbon and the 2 oxygens are about the same size, and so they don't exert more or less force on the electrons that they share. So the electrons tend to hang out kind of right in the middle between the atoms. That's a much more symmetrical arrangement than we see here with the unequal sharing of electrons. Here we have a water molecule that is V-shaped. The hydrogen atoms are much smaller than the oxygen. Oxygen therefore has a greater gravitational or pulling force on those electrons, and they hang out closer to oxygen most of the time, giving it a slightly negative charge. And since this side's slightly negative, because the electrons are hanging out over here, the hydrogens are slightly positive. We call this slightly negative or positive experience electronegativity. That's what that symbol is for. So the oxygen is slightly electronegative, whereas the hydrogen side is slightly electropositive. And this gives hydrogen not only unequal sharing of electrons, but poles. We would say that this water molecule is a dipole. It has a negative and positive, or 2 sides that are charged oppositely. Here's a quick guide for ionic and covalent bonding. Polar and nonpolar covalent bonding is separated. Remember, polar molecules do not share electrons equally. Nonpolar molecules do share electrons equally. And because polar covalent bonding produces a dipole, we will actually see something called a hydrogen bond that can occur between those types of molecules. Ionic bonding is going to be the transfer, not sharing, of electrons. And when dissolved in water, we see that the ions that are normally salts separate, and that's when we can visualize or see the charged particles. Sodium chloride is always a great example, with sodium becoming the cation and chloride becoming the anion. Let's look a little bit more at polar covalent bonds that do not equally share their electrons and create an electronegative and positive environment. Water is a great example because not only is it a polar molecule, but it's involved in hydrogen bonding, where we see these two different charges referred to as a dipole and contribute to things like surface tension and water strider bugs being able to float in water. A hydrogen bond is an attraction between a slightly positive side and a slightly negative side of a polar molecule, or a molecule that's functioning in polar covalent bonding. So the partially positive side of the water molecule with the hydrogen atoms can be attracted to the partially negative oxygen atom side as long as it's two separate molecules. So if we go back, ionic bonds and polar covalent bonds are happening between atoms. Hydrogen bonds are acting between molecules. So they're not quite as strong as atomic bonding, but together they can produce a strong force. So collectively, hydrogen bonds are strong, but comparatively by themselves, they're much weaker than ionic and covalent bonds. So we consider them a weak bond or an attraction rather than a true bond. They're between molecules, not atoms, so they're not really a true bond. But again, collectively they can be strong. They can produce things like surface tension. They also hold our DNA together. So here between hydrogen and oxygen, this would be a covalent bond. Here between the oxygen of one molecule and the hydrogen of another molecule, this is a hydrogen bond. And notice it's between the electronegative side and the electropositive side of a water molecule. Here's just another way to draw it. So the dotted lines are the hydrogen bond. Think of them as weak attractions, not true bonds. They tend to be between hydrogen and something else. Hydrogen and oxygen is commonly seen, but it could also be nitrogen or phosphorus. Here is an example of a water strider or a bug that is able to use the surface tension created by hydrogen bonds in water to float or skate across a pond. So let's try an example question. If an atom has 15 protons and 15 neutrons in its nucleus, how many electrons does it have? If you said D, you're correct. So the 15 neutrons part is a distractor. We're assuming that the atom is neutral because we're not told otherwise. And it says this atom has 15 protons, so to be neutral, it must also have 15 electrons so that the positive and negative charges are balanced. How about this question? The electrical attraction between positively and negatively charged ions forms a or an. You said ionic bond, you are correct. So electrical attraction between a positively and negatively charged ion is your key right there. It could say positively or negatively charged atom, and that would also be an ionic bond because it's between atoms, not between molecules. So hydrogen bond would not be an option here. How about this question? Which of the following describes a nonpolar covalent bond? So remember, nonpolar covalent bond is different from a polar covalent bond, which we spent looking at, Which of the following describes a nonpolar covalent bond? Remember, nonpolar covalent bonds are different than polar covalent bonds, which we spent more time looking at. That unequal sharing of electrons was characteristic of polar covalent bonds, so the best answer here is D, equal sharing of electrons. And one of our last topics we'll look at for this part of Module 2 is chemical reactions. Chemical reactions occur when chemical bonds are formed, rearranged, or broken. Chemical equations represent these chemical reactions. On the left of a chemical reaction, you generally see the reactants. On the right, you see the products. Reactants are substances entering into a reaction together. They may come together, they may break apart, they may rearrange. Whereas the products are generally resultant, and they're the chemical end products. They're usually located on the right of a chemical equation. And the amounts of reactants, the products, what their state of matter or the proportion of each is usually information provided in a complete chemical equation. Here are some examples of chemical equations. In both of these, we have non-reversible chemical reactions with arrows pointing to the right. The reactants in this type of situation are on the left and products on the right. Information that we're also given is things like whether or not the two hydrogens bound together on the right in the first chemical equation are a gas, solid, or liquid. And they're a gas, they're hydrogen gas. Sometimes you'll be given the chemical name and expected to know information about that chemical name. For example, in the second chemical reaction, methane is actually the name of a gas. So molecular formulas must be written correctly and balanced. Notice in the first chemical reaction where we have 2 hydrogen on the left and 2 hydrogen on the right, that we have the same amount that we started with on both sides. So we begin and end with the same amount of matter. That's very important because matter can neither be created nor destroyed, and all atoms must be accounted for and balanced. There's 3 main types of chemical reactions: a synthesis or combination, where we are taking small things and putting them together, like these amino acid molecules coming together and building a big protein molecule. These always involve a bond formation, and they're reactions that involve atoms or molecules combining to form larger, more complex molecules. In biochemistry, which will be our next topic, the smaller molecules are usually called monomers, and the bigger molecule is called a polymer. And the way they're put together is using anabolic or building processes that put energy or require energy to form and make a bond or to make a bigger thing. Decomposition reactions are another type where we have the reverse of a synthesis reaction. We have a breakdown. We're seeing the breaking of bonds and the releasing of energy. So these are exergonic, catabolic, or degradative reactions. Here we have glycogen, which hangs out in your liver and skeletal muscle, and it's being broken down from its component as a bigger polymer into small glucose molecules, which is what it's made up of. So this is a breakdown or degradative decomposition reaction. There are also some other patterns seen in chemical reactions, and that's the combination of synthesis and decomposition. These exchange or displacement reactions involve both synthesis and decomposition or anabolic and catabolic reactions, respectively. So we can see in the 2 examples that bonds are both made and broken. And even though this is a simplified example, if you were to do this in reality, you would make sure to always write the positive ion first. That's why sodium, as a cation in a chemical reaction, is written before chloride. The sodium is going to be positively charged and chloride negatively charged after the formation of an ionic bond. Here's an example of a exchange reaction, so where bonds are being made and broken. This is where ATP, which is molecular energy, is being or having its terminal phosphate transferred to a glucose molecule. This is called glucose phosphorylation, creating glucose phosphate from ATP, which is broken down into ADP, or adenosine diphosphate, because it no longer has 3 phosphates, it has 2. So ATP is broken down, whereas glucose phosphate is built. Looking at the energy flow in chemical reactions, we tend to see that all chemical reactions are either exergonic or endergonic, which you should remember from physical science. Exergonic is a reaction that results in a release of energy, whereas endergonic uses or absorbs energy. Exergonic reactions are catabolic because it's the breakdown or destruction of a bond that releases energy, whereas endergonic reactions are going to be anabolic because the absorption or use of energy make or can build a bond. And even though we generally write chemical reactions as going one way, they are actually theoretically reversible as long as situations and all the components that need to take place are present. As long as you have enough reactants or products, or vice versa, they're all theoretically reversible. Enzymes also play a role. The chemical equilibrium can occur if neither a forward nor reverse reaction is being favored or more dominant, So usually we do see one over the other. So many biological reactions are not very reversible because of the absence of reactants or products, or because the reactants once turn into products, we don't have backup reactants to create more product, or vice versa. Usually the products are then removed or broken down or sent somewhere else. So chemical reactions are usually a process, even though they're all theoretically reversible. So in summary, breakdown catabolic reactions are not only degradative, but they involve breaking bonds. We generally break bonds by adding water or performing an oxidative reaction called a hydrolysis reaction. And exergonic reactions release energy and heat in order to break a bond or be a catabolic reaction. And then anabolic reactions are synthesis reactions. They're a combination reaction. Generally, you would lose water in a dehydration synthesis reaction that is involved in making bonds. And they're endergonic, so they're absorbing energy, and the absorption of energy helps build bonds or make a process. And these are great examples of a type of reaction that not only requires energy to occur, but it's generally called active processes. And last but not least, let's look at what reaction rates are affected by. They are affected by temperature, particle size, and concentration of reactant. If you increase the temperature, you increase how fast molecules move. They're more likely to bump into each other, therefore react, and that increases reaction rate. If you decrease particle size, they can move faster, therefore again, more likely to bump into each other, more likely to react, and that increases reaction rate. If you increase the concentration of reactant, you will have a situation where the reactants are crowded and much closer to each other, therefore more likely to bump into each other and react, and that increases reaction rate. Catalysts can also increase reaction rate. Catalysts are things like enzymes, which can help hold reactants together in order for that chemical reaction to take place and produce a product. Catalysts are great because they increase reaction rate without being altered or chemically changed themselves. So they don't become part of the product, and when they're done, they get to persist or continue being catalysts for later or further reactions. So enzymes are a great example of catalysts that do this, that increase reaction rate by lowering activation energy. And that's it for part 1. So make sure you also watch part 2. And part 2 will be all about biochemistry.